Hello, everyone. We have a small issue. It will start in like 5 minutes. Hello, everyone. Uh, everyone hears me?
Yes, I hear you.
Yes. Okay. Thank you, everyone. Sorry, we have a small problem connecting the camera. It's gonna be resolved in like 2 minutes, but we can start on the camera. Share. Is it good? Okay. Gonna start in like a minute. Yes. Turn on the microphone too. Yes.
We currently cannot hear you on Zoom.
Excuse me, we don't have access to the voice of sessions. Could you please check it?
Uh, so now connect to the meeting, but with just with the video. Yes. See if that works. Connected. Second. Stay calm. Okay. No, how it works. Okay. Okay, I think everything is okay now. Okay. Would someone open his mic? Everyone hearing me?
Yes,
Yeah,
I
everything
can.
is working
Okay.
fine.
Okay. Thank you. Thank you. Thanks. Okay. We're gonna start. Okay. We're gonna start over. So, information geometry. We start with defining both what we mean by information and what we mean by geometry. And then we discuss why is it essential to study information geometry. There are online resources who people taught information geometry, but they're like seminars and talks. So no one delves into the whole information geometry thing, as well as the fact that there is a lot of background needed in differential geometry to study information geometry, actually. So we're going to try to study information geometry and teach it in a way that students without mathematic background could follow. Okay. We first start with, and feel free to ask whenever you want, whatever you want. So we first start by defining what is information and what we mean by information. We connect information to the estimation problem. And then we go and define what we mean by geometry and why considering geometry is a good way to tackle the estimation problem. And then we discuss a little bit about information geometry. Next session, we would delve into the mathematics of differential geometry. But first, we motivate why we need information geometry. Okay. First, we go through information. What is information? What we mean by information here is the minimum amount of bits we need to have to encode an event. For example, if we have a probability distribution P, the amount of bits we need is proportional to minus log Px. For example, if you have a coin, a fair coin, which is either 0 or 1, or heads or tails, you can encode this information with only 1 bit. So, for example, this picture you're seeing, the amount of bits it needs to represent, we call this information. So, if the probability an event is high, then the information it has is 0. Consider you're outside this room and you want to guess how many people are inside. So you have a prior belief system. For example, there are 2 with probability 10%, but you guess there are 10 people with probability 90%. If you come inside and have more information, or when you come and see 10 people, because the rare event here is seeing 2 people, then if you observe the people inside the room, because you observe a very rare event, then you have a lot of information. So by information, we mean Shannon information, entropy, and the number of bits we need to encode. Okay. Shannon entropy is a very closely related concept to this, which is exactly the number of bits we need to encode an event for a probability distribution, or whether discrete or continuous, Shannon entropy is given by minus expected of log of that probability distribution. Okay, these are some backgrounds, so we go here. So entropy actually quantifies the fundamental limits of how much information is needed to describe a random variable. As we saw, if entropy is high, the distribution is closer to uniform, so you have a lot of uncertainty. And if it is low, then you have concentrated events with high probabilities. Okay. Then we have likelihood. Consider we're observing an event with parameters set theta. And for example, you are in the first session, we're mainly considering normal distribution. Consider the data you have is coming from a normal distribution. So theta here is the mean and the variance of this event. The likelihood of one parameter is equals the probability of observing the data you observed given the parameter you chose. So we're going to have, for each parameter, we're going to have a number which defines how likely it is for the data to come from that parameter. And then because this is the multiplication of a lot of numbers, we're going to have log likelihood instead of just the multiplication. Okay. Then something very closely related is KL divergence, which is some distance. KL divergence is not a distance, but it measures how related the two distributions are. So if you have, for example, distribution here, and then you have another distribution here. Yes. And then Q. The KL divergence P with respect to Q measures the difference between the two probability distributions, which intuitively shows how much information is lost when we are using the second distribution Q instead of the first distribution P. Chat, something happened. Okay. Okay. And KL divergence is 0 only if the two distributions are equal, and KL divergence is not symmetric. That's also something to know. We're going to see other distances, actually. And also, the likelihood is closely related to KL divergence. These are some backgrounds. We're not going to discuss this too much. And then we have Wasserstein distance. Okay. For now, the whole idea of information geometry is that instead of considering each distribution discrete from the other, so I give you one normal distribution, you have another normal distribution, and you have another normal distribution. These events are happening completely independent of each other. There is no connection. We cannot measure how close they are or how far they are from each other. What can we do about it? So we need to add some distance, d, or some divergence to calculate how far they are from each other. As we saw, KL divergence measures the information between two distribution P and Q. But here, Wasserstein measures the cost. I will discuss about this. Consider you have a pile of sand over here. This is the distribution of the sand. And then you want to build a castle out of these sands. So you start from a distribution P over sands, and then you want to build a castle, which is a distribution, again, out of sand, but we call this Q. So Wasserstein measures how much effort you need to go from here to here. So, for example, you should take this amount of sand and put it over here. It's going to cost you. The cost is proportional to the distance. So it's very closely related to optimal transport, if any of you have heard. But the takeaway should be the KL divergence measure between two distributions, the amount of information. Information is the amount of bits we need to describe an event. But the Wasserstein distance measures how close they are, in a sense. Okay. Again, this definition over here measures the Wasserstein distance between two measures mu and nu, which is the infimum over all couplings. So the couplings we mean here, like the gamma, is the amount of sand from here, or any of these could be coupling. So in all the couplings between two distributions, which one gives you the least amount of cost you need to bring sands from the pile to build a castle? Actually, the most information geometry literature is about KL divergence, but for the application in finance and in machine learning, we're gonna discuss the Wasserstein distance in the last sessions, because to model finance applications, we need to go with second, not the information geometry. We're going to go with the cost geometry. Yes, we discussed this. And now we're going to see the relationship between these distances to the problem of estimation. Again, like any other estimation problem, consider you observed n samples, and okay, everything good? Yes. You observed n samples and assume that you know the samples are coming from a normal distribution, and then you want to estimate what's the best parameter is. As many of you who have guessed already, you're going to go with MLE, maximum likelihood estimator. Also, we're going to see how these distances and divergences play a role here to estimate. For the start, I will go through maximum likelihood estimation, which I think every one of you is familiar with. We start with the likelihood. We take the logarithm of the likelihood, and then to optimize this, we want to find the maximum likelihood estimator. We take derivative with respect to the parameters, we set them to 0, and we get to these two numbers. So it is unbiased estimator, so the mean is going to be the empirical mean, and the variance is going to be the empirical variance. Okay. Now, we're going to see how this geometry, although we're not defining it very formally here, plays role here. So we start from observation. We have train time, observation, distribution. And then we have the space of all normal distributions, parameterized. And then we want to sum with this distance and divergence we introduced, find the closest distribution to this. Okay. So we started from P hat n, which is the empirical distribution. So you observed 1 over n. This is the empirical distribution you have. It's over here, and this is the space of all normal distributions. We show it by p theta. Okay. What's the best distribution you can choose? So consider you have no geometry or distance. This is impossible. But if you assume some distance, so you're gonna measure all these distances and then go with the one that minimizes it. So the funny thing here is that the distance is going to change if you go with KL divergence or if you get with Wasserstein. So in Euclidean geometry, consider for now, forget about all this KL distribution and everything. What's the answer to this problem? You're going to find the perpendicular to this hyperplane, if it is a hyperplane, which we'll see it is a hyperplane, and this is going to be your optimal p theta star. Okay, so in order to go for the geometry, we need to have angles and we need to have distances. We already have this, but we need to somehow define angles. That's what Riemannian geometry is. So before all that, let's first go and compute the KL minimizer. So consider that space with the distance of the divergence, KL divergence, and we're going to find the best approximation we could. So if you compute this, you'll see that exactly KL divergence gets to the maximum likelihood estimator. Why? As we discussed here, as you can see, the likelihood, which is the left-hand side term, if this is going to get maximized, then this should get minimized. So KL divergence geometry is exactly that one which gives you the maximum likelihood. There is another thing I want to mention too. So consider again, remember the example of the students in a class. You have a belief, which here translate to you have a belief that the data set is coming from a normal distribution. And then the maximum likelihood estimator actually here gives you the best parameter set with considering as much randomness as you have. So you're not going to assume anything else but the thing that the parameter is coming from a normal distribution. So that's an intuition we got from KL divergence. If you remember, KL divergence says if you have the training distribution, I'm going to find the best distribution with the least amount of information loss. So MLE actually very closely related to the information. Then we have the other distance. Here, if you consider the Wasserstein distance, I won't go through the calculation. Just take it from me that the distance between two normal distribution is given by the Euclidean distance. So it's like we're considering the geometry of distribution, normal distribution, to be the same as 2D Euclidean geometry. In 2D Euclidean geometry, you don't have any curvature, everything is straight, and the distance between these two is exactly given. So if this is mu and this is sigma, the distance between two distribution P and Q is given by that. So if we minimize this, one could see that the answer is different. Actually, the variance answer is different. So we already built two different geometries that gives two different aspects of an estimation. Which one we should use? So why to go with the minimizer of Wasserstein distance, or why to go with the KL? If you want to measure, for example, in machine learning, in every application, in most of the application, if you want to assume the least, you want to have the least amount of information loss, you should go with the KO geometry here. But otherwise, Wasserstein is the answer. We'll see what applications these have. I couldn't come up with a simple example that not going with the least amount of information loss is actually beneficial, but it's good to think about this too. So here yes, this is the simulation. Consider the bar distribution as the samples we saw. So this is the empirical distribution we came up with. And the true distribution actually was the green normal distribution. Then if we find the MLE, which happens to be the minimizer of KL divergence, we get the blue. But as you can see, the red distribution is the answer of Wasserstein distance. If you want some intuition, consider again the red as the castle and the gray area as the sand pile. This red distribution is the distribution that leads to the least amount of force you need to bring all this behind this, below this red distribution. Okay. So here in the first section, all I want you to know is the close relationship between KL divergence and information, what we mean by information, and what is Wasserstein distance. Yes.
So, Wasserstein distance, sort of underestimating the variance.
Exactly.
Is that related to how the empirical data is given, or like is it just how the Wasserstein distance formulates the problem in a way that it sort of removes some information from the variables?
Yes, actually the second one. So the question is why the Wasserstein estimator underestimates the variance. Yes, because it gives away some information you have just to find the best solution you need. Actually, the optimal transport problem we're here discussing, the amount of force you need to, it's one of the most studied in the whole area of mathematics, because consider any applications. You have some resources, you have some products, and you have some people who want to buy. What is the best way to bring this stuff to the buyers? So you don't care if you are sending products to someone to somewhere with a lot of products. As long as the effort is the least, you're good. Yes. Any other questions?
So I had a question. Actually, we use Wasserstein too with changing the number of the washer. Like if we use Wasserstein 5, would the result differ or would it still be the same and it would underestimate all the time?
So not all the time, but the same as what you mean?
Like I mean, if we change the, if I remember correctly, the Wasserstein distance had a variable p, and it was related to the p that we choose. So would changing the p actually matter in the underestimation that it has?
The P. So, this you mean?
Yes, actually.
Yes. It is very closely related to the variance underestimation, because we are considering P to equal to 2, but we can go for P equals to 1/2, then it would overestimate the. It's very closely related to the ball, to the. So this is the P2 ball, and this is all P1, P equals infinity ball. But as you can see, if we go with 1/2, the ball is not anymore convex. So actually it is not true distance. But if we go with this, and there are ways to define the geometry with P under 1, then you're correct. We're mostly are gonna end up with overestimation of the variance, because if you go with this, it's like going out, moving the sand outside the castle would not penalize you as it would if you go with P more than 1. So it's okay. I will overestimate the variance.
So P dictates how the cost is spread over the distribution.
Yes. Yes. And yes, instead of this Euclidean type of distance, you can come up with any cost, but normally people would go with cost equal x minus y to the power of 2. Puya is okay, everything?
Yeah, thank you.
Okay. So here we go from the information. We have some distance. We're gonna need the angle and curvature. So geometry. What we mean by geometry here? Consider the simple gradient descent algorithm. So at each point, from a random point, you start, you take the gradient, you take a step toward that, and you do the same. But as many of you have seen, you can go with a smarter way, Newton method, which consists of considering the second derivative of the function. So instead of going with the update rule as simple as taking the gradient, so at each time instead of going with this simple thing, you add 1 over the second derivative of theta. I think it's squared. y. So what does this actually mean? It's literally the definition of curvature of a curve. So you're going to say if the curve is not curved, if the graph is not curved, I'm going to move a lot. But if I'm here, as if I move a little, the surface is too curvy and I would be far from where I've started. So as you can see in optimization, we need the curvature. So the two word geometry, optimization and curvature are very closely related, as it was for information and estimation. Okay. Okay. So as you can see, I would go with the Hessian, which is the second derivative. And yes, in one, because the function is, it's like some cheating, because the function is convex, just wherever you start, you end up with the minimizer point in just one step, because this is the definition for the convex case. But anyway, this is something you could do. For example, here is more interesting. Let me first, yes. Consider you want to minimize the function f constraint with the surface of a torus. So you're going to find the minimizer on a constraint. So the gradients, the gradient descent algorithm, which here is shown with the red dot, going to take the gradient and does not consider the geometry of the underlying constraint space and go just over there. And then after each step, you're going to project yourself to stay on the torus and then do this again and again and again. But if you go with the second method, which is taking advantage of knowing the curvature of the space, you're going to end up to the optimization point, optimized point, much faster. Consider, so actually, what is the green line here? Yes, but so we have a green which is curved. This is to some extent the best trajectory you could go starting from this point. You could, this is some kind of the best thing you could do. Okay. Consider this. We have a very heavy object here. And then you have a lamp over here. You beam a light. Okay. Why doesn't the light go this way? As everyone may have guessed, because this object curves the space-time, if I'm correct, and it goes this way. Okay. What we call this? This is some notion of least distance or straight line. So anyone have guessed what we call this on any surface or on any curve? We call this geodesic. So in Euclidean geometry, all the lines are both the shortest path and the least curved path. But the funny thing is that we do not need the least distance. If we go naturally, we automatically go with the least curved one, the most straight one. So as we'll see next session, formally we define geodesic in a manifold. As one would see, this second, which we started with some adding some curvature to the optimization problem, this is actually the geodesic of this torus. Question? Okay. So
You haven't defined what method gave us that.
yes. So at each point,
No, you don't, the manifold optimization thing, you haven't defined that yet, right?
not yet, but here how I got to this graph is just to take the curvature of the surface into account. So at each point, so you have f and you have the constraint. So at each point of FUR at time t plus 1 is going to be t minus eta gradient of f. Here we're going to assume at the curvature of the constraint space. That's all I did. So it goes through the geodesic. What geodesic? You started with the sum point, and then this was the optimal point. It goes the straightest possible way. This is the yes, but the manifold, not yet. We're not yet discussing. Okay. So the geometry we're discussing is mostly related to the distance and curvature. And we're going to take advantage of it into the optimization part. Okay. Yes. So from now on, why we go with the geometry? Because we want faster optimization. Why we need information? Because we need estimation. So information geometry is, in another terms, faster estimation. So in order to go faster, you need geometry. Okay. Okay. Now we're gonna define Riemannian manifold. This is going to be a little too much for people who haven't studied manifolds yet. So I try my best to define manifold, then differentiable manifold, and then we're gonna continue from there. What is manifold? As the name suggests, it's some surface, some space that is folded many times. That's literally the name. So we're gonna go with a surface. So this is a manifold. A torus is a manifold. Why? Because it is a surface which is folded. The Euclidean space is also a manifold which is not folded. So to define this, in some extent, manifolds are the extension of Euclidean space. Consider you are in Rn, and then this thing that we're gonna formally define as manifold is you start with open set U and some coordinates here. Then if you cut the manifold locally, if you have an open subset of the manifold, then it's going to locally look like the Euclidean space of dimension n. We call this charts, and these are the coordinate systems. So at this other cut, you are going to have some other open set B that goes with the same to here. Okay. And yes, there are lots of some good stuff. So we assume everything to be as differentiable as it is. And we assume, for example, if we have two open sets and these here have intersection, then everything is smooth and everything agrees on this. If you go with this chart, if you go with this chart, everything gonna be the same over the intersection. So we're gonna assume all of that. We don't need to go to the details. If anyone is interested, you can study manifolds. So by manifold, we mean an n-dimensional space which locally at each point looks like the Euclidean n-dimensional space. And by smooth manifold or differentiable manifold, we mean these coordinate functions to be differentiable, smooth. If the manifold is topological manifold, these to be just continuous. So that's what a manifold is. There are lots of, you can go with lots of examples. For example, consider circle is a one-dimensional manifold. How? This is my one-dimensional R1, and this is 0, this is 2 pi, and what I'm going to do is to go and put as phi of theta, and then generate this. So it is going to locally look like a line which is curved. That's a manifold. Also, the Rn is also a manifold with charts being open sets and with identity, a function to be the coordinate system, to coordinate functions. And yes, this is the manifold. Question? Okay. Then we need some extra structures on manifolds in order to understand the geometry. Vectors. So in Euclidean space, let me first formally define vector bundle. So you have your manifold, which I show it with n. It consists of charts and the dimension considered to be n. So it is a collection of points at last. So what is a vector bundle? At each point, you're gonna stick the whole Rn Euclidean space onto here. So the vector bundle at point P of n is gonna consist of all P and V's, where V is in Rn. So vector bundle at each point, we defined it for each point to be sticking the Rn dimensional to that point. Why? Because these are here the vectors. Later we'll see how these vectors are going to give us the angles we need, the distance we need, and everything else. But for the first session, these are just some intuitions I'm going to give you. For the next one, we'll dive into the all details of manifold. And also, so in Euclidean space, the basis, so this is a vector space. of what dimension? Obviously, n dimension, each vector bundle of each point. So for Euclidean space, each vector space could have a basis E1, E2, En, but here, as we'll see why, we show the basis of each vector bundle with so what is this? If you remember, we started with charts and mu. This is the C's we had. So the basis of the vector bundle at each point, the tangent bundle of each point is going to be n dimensions, which we show, the convention is to show this by these vectors. Okay. Let's forget about this. Now, this is the whole idea of Riemannian geometry. So, we already defined points on a manifold, and at each point, so you cannot add, for example, this vector with this vector. Why? Because they are on completely two different spaces. So at each point, we have a vector space, we call it tangent bundle, and then we define the vectors over there. Now, if you remember, we decided to define the angle between points, between vectors. So we already have vectors. What we can do is to define angle between them. By angle, what we mean is an inner product. So for example, in Euclidean space, what's the angle between two vectors v and u? It's going to be the inner product this is the angle. So for the angle, we already have a norm on this space because this is exactly Rn. And we need to define inner product. Okay. The thing that makes Riemannian geometry completely different from Euclidean geometry is that this inner product, now we show it by G of U and V, is dependent on the point itself. So for each point on the manifold, we're going to have a different inner product. And we'll see the idea, the underlying idea here is that with this, we're going to define the curvature at each point. And then the curvature would rely on the point itself, because the inner product is gonna depend on the point itself.
These are influenced by the basis of each point?
That's a very good question. So first of all, as you saw, we defined the manifold with one coordinate system. One may ask, what if I go with another coordinate system? The whole idea of manifold is that there are some good conditions, which is not hard to find because this is phi going to the manifold. And if you have another coordinate system with like and p and rho, the whole idea is that this combined with this function, So if we have psi of I minus, this is also smooth. So everything is good here, and the idea with the inner product is that it is invariant. Exactly, it is invariant under the change of coordinate systems. Because as you can see, we just define it on two vectors. But if we show the vectors with different coordinate systems, it's gonna give you the same angle.
I was just trying to understand, like, you have P for every point, right?
Yes, for each.
That separation is only for just for the sake of separation, that you can't do them, like, have a dot product, or is it something else?
No, the problem is to have P is that the vectors themselves are stick to the point P. So you cannot discuss the angle between two other vectors.
And that is what P signifies.
Yes. And at each point, we'll see that this inner product, how it would relates to the coordinate system. Okay. And then if you have the inner product, as you saw on every calculus class, you can define the distance between 2 points. So the distance is gonna be the infimum over all curves that goes with from the point A to point B, and how you're gonna compute the curves the curve's length. It's gonna be the inner product. For example, change this to Euclidean geometry. This is nothing but the integral of norm of the derivative of the curve. Here, because at each point we have a different inner product, so it's gonna show up like this. So if we define the inner product, we're gonna have distance. What we saw earlier with the Wasserstein distance and the KL divergence was that we started with a distance. Does that define an angle? We'll see in a minute that that's another thing which is very interesting. Okay. Okay, so by now we defined what we mean by geometry, which is a bunch of points with an inner product on each. And then this inner product would induce a distance between 2 points. We couldn't be without this. Without this inner product, you couldn't find the distance between these 2 points. You could define your Riemannian geometry with some other coordinate system, and without this inner product, the distance would change. For example, in the circle, I could generate any the distance between 2 points on a circle would start to get higher and larger and larger if I change the radius. We need something to fix the radius. And what's that? The inner product on the circle. So circle may be a misleading example, because circle is already, when I say circle, you already assume it to be in Euclidean 2D space. But consider a perfect circle, which is not embedded in any dimension of not in the 2D dimensional Euclidean space. Here, I did not assume that this to be embedded on a 3D space. It could be any manifold. As we'll see, the manifold of distributions, it cannot be embedded anywhere. So when I say circle, consider a circle without the circle being embedded in any space. How you gonna measure the distance between 2 points? Because you don't have any measurements. You are not embedding it in anywhere. The amazing part is that if you define the inner product without even embedding the manifold, you're gonna end up with the distance between points which are not embedded anywhere. It's just some mathematical convention. So you can define it. Okay. That's also something I wanted to mention. So if you consider spaces embedded in other spaces, that's called exterior geometry, which you have the space globally. You have access to the space. You can go anywhere because you already embedded it in some space, and that some space is Euclidean space, and you can define whatever you want. That's exterior, but Riemannian geometry gets very interesting with interior. Not exterior and interior. Explicit and implicit geometry. The implicit geometry here is that it's not embedded anywhere, but still we cannot talk about the angles, we can talk about geodesics, we can talk about the distances.
There is no frame of reference.
Exactly. Now we're gonna discuss a little bit about information geometry. Okay. Now, also, yes. Now we're gonna embed actually the space of all normal distribution and call it the manifold of normal distributions. So consider this space. This is a manifold. Why? At each point, you can have the identity map. So this is R2, and this is the space of X and Y equal this. This is a manifold, true? So we're gonna say the space of all normal distribution equals this. How? We say, consider this as the mean of the distribution, and this as the variance. And then each point would be a distribution. But what is the distance between these two?
Yeah.
Okay, we can go with any distances, true? If we remember, if we define a distance, it would induce an inner product on each point.
Yes.
And if we start with the inner product, it would deduce distance, true? Okay. And the funny thing here is that, as we saw, this, if we consider this as the distance, this is nothing but the Wasserstein distance. So Wasserstein distance is to consider Euclidean geometry with no curvature and anything. So the inner product at each point is simple. We already know about that. Okay. But what is the distance? If this distance is KO, then what is the G at each point? Okay. and it's already on here. So Fisher information metric, which I defined here, is the inner product here. So let's see this. Just to go with the details of this. We're gonna get into this later in the course in the next 2 sessions. But if we start with defining the inner product, so inner product of U and V is gonna look like U transport A, call it G. This is the inner product between the 2 vectors. Now it's gonna depend on the point. So the G is gonna depend on the point. The G should be symmetric, positive, definite, and everything to make this an inner product. It is an inner product if and only if GP is positive semi-definite. So we need to define GP, G sub P. And it's gonna look like that. So at each point P, we're gonna define GP, which is a matrix. It's gonna be the expected value because we're going on a distribution of the derivative of log likelihood log P so just before making things complicated, we can go for the log likelihood of a normal distribution. We take derivative with respect to mu, it would give you this. And then you can take derivative with respect to the variance, and it would give you this. Then you need to multiply this. And then if you consider the terms, he's going to cancel out and become 0. And here we're going to have 1 over sigma squared and 2 over sigma squared. So we already found the inner product at each point. Take a look at here. So if I make mu constant, for example, equal to 3, if I change sigma, or I make sigma constant equals to 4, and look at this line. These points all have the same variance. If I take a look at the Riemannian metric, which is the GP here, which is the inner product, as you can see, it does not depend on mu. So it's going to be the same for all of them. But if I take a look at this line, as you can see, when it gets closer and closer to 0, the inner product gets bigger and bigger. That means it has a very, very large, in altitude, curvature. It is negative, so it has negative curvature, so you cannot imagine it because it cannot be embedded. It's gonna have like this Klein models of hyperbolic geometry, not Euclidean geometry. But as you go further to 0 variance, the curvature explodes. So the distance between 2 points, for example, these 2 distributions in this geometry should not be this. It should be curved. So before going further, let's assume you have, this is sigma, this is, let's assume you are going from this distribution, which is -3, to this distribution, +3. So the variance are equal, true? So everything looks the same, but I just shifted the distribution. So what is the closest path this could go to over there? Let's see. If it wants to go downwards, you're actually taking a very bumpy curved line. Okay. If you go straight, again, this is one option, but the best option, just heuristically, just by intuition, is going to be this. Why? Because you go as further as you can into the space which has smaller curvature. Remember, as we go to 0, the curvature explodes. So we can manage going a little downwards and then going upwards again in the curvature. So it's gonna have like, it's this thing here is a very heavy object. So it's gonna curve over there in order to avoid this. We'll see in an example, numerical example, how really this is gonna take this. Okay, this is the inner product of Fisher information, which is, if you start with this inner product, you'll end up into KL divergence. And as we saw, the Wasserstein inner product would look like usual inner product, which is the usual inner product of two vectors. So it considers no curvature over the space. Now we'll get back to our example, the same example of estimation. We're going to see how information geometry solves this. Consider you have 100 points. Again, you sample them, you observe them, and then you're going to estimate the normal distribution that these samples came from. Okay. But here, instead of using an estimator, you're gonna start from, so your data points came from this true distribution, and consider that the empirical distribution is here. It is not on the same manifold, but consider this to be the true distribution. You start from some estimation, some done estimation of mu hat and sigma hat. Okay? So how you gonna optimize this? The same as gradient descent. What was the problem with gradient descent that we didn't? So consider this. Mu hat, the second time is going to be mu hat. The first time minus n, what? Gradient of what? So it's going to be, because you were maximizing the likelihood, true? It's going to be likely. Yes? So you could get, and you had 1. And you would get to the result. So this thing, because it does not capture the curvature, it's going to be look like this. Okay? But if we include the curvature, now we have everything. We have curvature at each point, and we take into account the curvature to update this. So we put here the curve. Then it would go faster. and converges faster. This is one way of looking why information geometry, which this method, instead of gradient descent, is called natural gradient, which Amari introduced. Amari is the founder of information geometry. This is one way of considering why information and how information geometry works. Also, I included some other graph. So here, look, if you want to go from this distribution, which was the estimation you started with, to go to this distribution, which is the true distribution, if you want to go the best path to the least amount of information loss, it's not just moving everything left. It's to increase the variance of the distribution and then decrease the variance. Whereas if you considered Wasserstein distance, it would look like this. The intermediate steps would be like this. And last, this is also some experiments I did. So you can see the blue distributions. If you consider the Fisher information geodesic, it's going to be curved, but as you increase the variance, it's going to look more flat. Yes. So the problem with Wasserstein geodesic is that with it does not take into account that the variance is too low. If the variance is too low, then you are estimating something which means you have a lot of information, something like this. So you're gonna move carefully, but it does not care if it is this or it is this. It moves. It does not take into account the gradient, the variance. Yes.
With this going up, you essentially sort of, if you think about a Gaussian, you go up essentially, you expand it first, so that you sort of envelop the true one inside you, and then you contract towards the true.
Exactly.
And doing so that, and this whole mechanism sort of preserves information.
It does not. You lost information starting from here, starting from this to this. You are losing information, but this path guarantees you lose as least as information as you could at each step.
And the least necessarily, is it that I am more flexible to be more aggressive in terms of how fast I'm moving?
Exactly. Like, consider you're optimizing a function like this. If you are close to the minimum, you should move very slowly. But if you are here, you should take a steep, big movement.
So in this example, the second curvature is not exactly the same as the first one after the movement.
It is. The variance and everything is the same, just the mean. The amount of information lost in two cases are the same. Is about the path we took that made it. Because if you go with the first method or Wasserstein distance, the two distribution you get at the first and at the end are the same. So the amount of information you lost is the same. But the path you chose was faster with respect to this geometry. If you consider another geometry, which is Euclidean geometry, then of course the Wasserstein trajectory was faster. Yes. And yes.
The concept of being fast here is linked with how big of a step you can take.
Yes, consider the curvature as the gravity. So if it is so much curved, you cannot move. So you need to, every step you take is more slowly. That
If you're
I
going
mean,
straight.
yes.
Okay.
That's what I mean by slow.
So the information where you're getting from the gradient actually suffers
Yes,
if you're taking the straight line path.
exactly.
Okay.
Yes. So, any questions? Okay. So, in this first session, I hope that I motivated you that information geometry is important. More than important, it is beautiful. Because now, instead of having distributions, you kind of have some geometry, something that connects them. You can go from one distribution to another distribution and look at the intermediate distributions you have. I defined what we mean by information, what we mean by geometry, and in the next time, I would delve into more details of differential geometry with more definitions. And later, in the last two sessions, we would go to see the applications in both learning and finance. Yes. Okay. Question? Sorry. Couldn't check the chat.
Excuse me, I have a question.
Yes.
Is there any applications of information geometry in reinforcement learning?
Yes,
I mean, modeling the
I
problems.
I'm not sure, but I saw some review paper that discussed the applications of information geometry in reinforcement learning. Also into the reward function of reinforcement learning, the most information you want to take into account, the most information that is represented at each state. So in that way, it's kind of related. Also, I'll take a look and let you know, but I'm pretty much sure that it has strong relation and application in reinforcement learning too.
Thank you very much.
Okay, and also let me know if you want to go with overload mathematics or you want to go like shallow mathematics with just code and see the applications. I'm more interested in the mathematics, but we can go either way. Okay. Done? Question? Thanks.
Yes, thank you. I think it needs more mathematics in state representation learning in reinforcement learning, and we can talk about it later. Thank you.
Sure. Thank you. See you all next week. Hello.
The record